Okay, so I told you there's two pieces to this. One, the first half was just, you know, how do you get around, step around maybe a professor that says, find for me the Cayley table of D8. There must be an easier way than actually saying, I'm going to take the octagon and look for every single rotation and every single reflection and then put them up and then multiply all the pieces together and fill in the Cayley table. There's got to be a better way than that. Now we have that. The second part of this is to extend the idea of a generator. So the cool thing about a generator for cyclic groups is that once you know something's a generator, all the other elements are not important. You can just take powers of that one generator and it tells you everything about the group. And this is how mathematicians think. In Calc 3, you had I, J, and K. They were important. They were the only important things. Everything else was a linear combination of them. In linear algebra, you had the basis vectors. In Calc 2, polynomials were used to approximate any continuous function. That's called a Taylor series. Right? So the polynomials are like, that was like the aha moment of why polynomials are so important, why you spend all this time talking about polynomials, is because they approximate any continuous function. Stone-Weierstrass theorem, you should have got that in real analysis. The coolest theorem. That's the coolest theorem. No, I think spectral mapping theorem is the coolest theorem, but it's the second coolest. It's a very cool theorem that you really have the rationals. They approximate any real number. That's really, really super important. So the real numbers are not as important because I can just approximate them with a rational number. That's what your calculators do. If you put pi in there, it is approximated. I can get as close as I want. The rationals are dense in the reals. So these statements of things that we have all the way along in mathematics, you might not have thought of it that way, but you see kind of a pattern emerging the more mathematics you take, that we always kind of look at anything that we have and say, what's really important in there? Can I pull out 2 or 3 things that are really important and just focus on them? Eigenvalues. Yummy, yummy stuff. So you have, in linear algebra, linear transformations, lots of them. Some rotate, some stretch, some scale, some do all combinations of them. But I can represent this sometimes by a matrix if I have an n by n one. And from the matrix, there's one important set of numbers that I can look at, which is much easier than looking at the box of numbers, called eigenvalues. I now have a direct mapping from n by n matrices to the complex plane. And you spent some time playing with the complex plane. You know that better than you know boxes of numbers. So we do this all the time. So in this generator thing, it's a big deal because if I have a cyclic group, I've just got one element. I just need to know that one element. I don't need to know anything else. Not all, but the problem is not all groups are cyclic. In fact, Dn's not cyclic. Think of that structure I just showed you a few slides back. There wasn't one element I kept taking successive powers of that it gave me all of Dn. So Dn is a non-cyclic, finite, non-abelian group. It's an interesting example. But your homework is going to lead you to the conclusion that you can express Dn maybe not as a power of one element, but a power of two, combination of powers of 2 elements. So really that's telling you what are the 2 most important elements of Dn. What are they? The first reflection and the first rotation. That's all I need to know, and then I can create for you the entire Dn. With R squared, some properties though. It's not just that I have this, there's some restriction. So if I had this, that all things could be expressed this way, and I also had the property that R squared is equal to the identity matrix, and that R to the n is also, you know, if I rotate n times around, that's another special property of these dn's. And I have this last property here, I can create you the Cayley table. From this information and this information, that's all I need. I can create the Cayley table. You just try. You can do that. You can do D8. Try D8. From this information and this information, you can create D8. You don't need to draw the thing or do anything. So it's not just that I needed this, I also need those restrictions, those special properties. So in a way, this little r and this capital R, they generate all of Dn with those restrictions, those constraints. So a subset of a group generates G. So if this is a subset. If every element is G, can be written as a finite product of those elements in S. It's a little bit more than just a cyclic group. Cyclic group is only one, right? So the little a, it's only one thing. Here I have a whole set. And if I know those elements in the set, they can generate that whole group. play around with the 4-Klein group. So the 4-Klein group is not cyclic. Do you agree? Why is it not cyclic? No one element, right? Every one of the powers, if you start trying to make one of the group elements a generator, what happens? Get the identity too fast. So if you take a squared, you get e. B squared gives you e. C squared gives you e. So there's no way that one element in the 4-Klein group can generate the whole space, right? There's no way that's going to happen. But is there a way that I could take a combination of 2 elements, like I did with the dihedral group, and use those 2 elements to create? The answer is yes. The elements in S are called the generators. I think this picked it up that I gave the answer. If you're really into math, you're thinking, can that always be done? Can I always take a finite group and get generators that are proper? Not the whole thing. The whole thing obviously will work, right? Can I always get a subset that's proper that generates? I don't know. If you have a long commute back, you can think about it. Actually, I had to call Dr. Lee. I said, I'm making up problems I can't solve. I'm making up problems. I don't think I can solve this quickly. So springboarding off the dn, the whole construction of dn, if I know the generators are in little r and capital R, and I know the constraints, those were the constraints. With this minimal information, I can create the whole table. Then this is all I need to know to construct the Cayley table, right? If I know the generators and the constraints. That is, I have the group from this information. It's that mathematical way of thinking. I just have a few guys that tell me the whole thing. So the structure of G can be fully described by the generators and their relations. That's called a presentation. It's not a representation, it's called a presentation of the group G. So an example of how we write that is we put the generators up in front. The symbol is just like we had for cyclic group, except the 2, now that I have more than 1, there's 2 generators here. There could be 3 or 4, who knows? In the case of dn, there's 2. And then all the constraints are written here that I need. So those are the relations. Now that is how we express the presentation. So it should make sense. You're just expanding the idea or extending the notion of generators. Just like why it's important, like once you know something's cyclic, it's cool because now to write your proof, you just take, let's assume G is cyclic. Let A be a generator of G. And then you just work with A and you prove whatever you want to prove. So it makes the proof easy. So that's why we do this. So if we have to prove anything about an arbitrary group and I know it has generators, I can just work with the generators, and instead of working with 10 or 15 or 1,000 elements, I'm just working with 2 or 3. Okay, so this one's not easy. Play around with it. I told you the answer is yes. The answer is yes. You're going to find that there is actually a product that you're going to be able to create the 4-Klein group. Figure out what the restrictions are. Scratch around. And I call it play because it actually feels like the same way I feel like when I'm playing with Legos. It's play. Just play.
The presentation isn't unique, is it?
I don't know. Better not ask those questions because I might assign it for homework. No, I don't know. Now I would think not, right? Because if you take the cyclic group is an example of a presentation, right?
Oh, yeah, okay.
So if in that basis case, but another question would be, what if you took and excluded just cyclic groups from presentations? Would it still be unique, or would it be unique? My gut feeling is no. Okay, any other questions? So I do have 20 more minutes, I can go over the advanced slides. If it's above, if you feel like the language is different too. So if you feel like it's above you, it's not going to hurt you. It's not going to hurt you. I'm not holding you to it, responsible for it. Sometimes there's been cases where I've been in classes, graduate classes, where they beat me up bad in there. They made me do all the homework and they made me do everything, and I come out looking like I was a meth victim. But there's some classes where they didn't make me do anything, and I spent the semester just watching. And I gotta tell you, I did get something out of it. Maybe not as much as the beat up sessions, but I did get something out of it. So the second time you see something, you can say, I've seen it before. Oh, I kind of remember I've seen that before. So don't be frightened of like the language. So this is the advanced stuff. This is on permutations. And I would read Fraley just to give yourself some background, because I'm not using Fraley. I'm going to a different, not the book that I just showed you. I'm going to a different book. But the section on permutations in Fraley gives you a basic understanding. And if you already had permutations, it's probably just review anyway. So you could probably read it and you'd be fine. So just to remind you, sometimes these notations look scary, but really, if you're looking at something like an R cycle, that's where a permutation cycles back to itself. You need to take one goes to 2, 2 goes to 3, 3 goes to 6, and 6 goes back to 1, and you call that a cycle. So this is the notation that we use to describe what is an R cycle. We have I1, I2, and IR be integers in 1 to n, so I'm permuting n elements. If alpha is the permutation, so I'm taking these 1 through n, I'm moving them around, and alpha is the function that moves them around. And it fixes the other integers in there, if any. And if I know that alpha I1 goes to I2 and alpha I2 goes to I3, and just like I told you with the example, 1 goes to 2, 2 goes to 3, 3 goes to 6, 6 goes back to 1, then, and in R steps it does that, then it's called an R cycle. And we also say that alpha is a cycle of length R. And this is in Fraley, actually. He does talk about cycles. I'm not quite sure if he uses math notation to talk about it, but it's talked about in his book. A 2-cycle interchanges 1 and I2, and it fixes everything else. 2 cycles are also called transpositions, and that's definitely talked about in Fraley. Permutations, which are just permuting n integers, can be factored. What's beautiful to me about permutations is they're a replica of the integers. You know, integers, you have factorization, and you have the fundamental theorem of arithmetic. If you were in number theory with me last semester, I got really excited about things like that. So you can take you're really breaking down to prime numbers. So in the same way, you can take permutations and factor them. And this is a mirror of what we do for primes. So, and there's an algorithm. And the algorithm is pretty simple. You start with 1. So this is a permutation. If you haven't seen this before, or it's been a while since you've seen it, the idea is to express your permutation as, here are my first 9 integers, for example. This means that 1 gets mapped to 6. You're just permuting the order of where everything goes. 2 gets mapped to 4, 3 gets mapped to 7, 4 gets mapped to 2, 5 gets mapped to 5, 6 gets mapped to 1, 7 gets mapped to 8, 8 gets mapped to 9, 9 gets mapped to 3. A permutation is just a one-to-one and onto function. There's no doubling up of numbers here, and everybody from 1 to 9 got a hit, right? So we start with the beginning, start with 1. 1 went to 6, but then 6 goes back to 1. So there's a 2 cycle. So the first cycle is 1, 6. Step 2, you go to the next number that wasn't in your first cycle. That's 2. And then you do the same thing. 2 goes to 4, 4 goes to 2. So that's my next cycle. I copied and pasted, so you don't have to copy from the previous board, but I can keep going. And if I keep going, if I look at 3, 3 goes to 7, 7 goes to 8, 8 goes to 9, 9 goes back to 3, and 3 goes to 7. So I have this cycle right here, right? That's a 4 cycle. And then 5 went to 5. So it's a loner by itself. So in this way, this is what I mean by factoring a permutation. You're taking the original permutation and writing it into pieces. So disjoint permutation, you can always take a permutation and make things that are overlapping, like the 2 appears in twice in a cycle, you can always do that actually. But we're interested in permutations that are factored into disjoint cycles like I just did in that algorithm. So if you have a permutation that's disjoint, this is the mathematical way we describe disjoint cycles. So you probably haven't seen that from Fraley. Sometimes the difficulty in mathematical exposition is to take something that everybody can see as an obvious and then write it down so that someone can read it. And that's what that description in that previous illustration was, right here. So if you're trying to do this homework, you have to do the other homework too, because it's playing around. I want you to do that. But if you're doing this homework too, develop an example of 2 disjoint permutations and describe how they satisfy the above definition. That's usually what I do. When I get a mouthful like this, I immediately try to make up some examples. Make up examples and show me how it works. What the J is, and what the beta is, and what the alpha is, and how it satisfies this part. So all the pieces. Show how it works through the definition. And walk the reader through. Here's where this is, here's where this is, here's my 2 examples, and so forth. Just walk them through, and this is how the definition works, how it identifies with all that crazy notation. Disjoint permutations commute, that's cool. Every permutation is a cycle or a product of disjoint cycles. So it's either a cycle to begin with. 1 goes to 2, 2 goes to 3, 3 goes to 4, or it can be factored into a product of cycles. And this factorization is unique up to an order of permutations of the disjoint cycles, just like factoring things into primes. These are the primes. The cycles are the primes. It's cool. A complete factorization is a factorization of alpha into disjoint cycles that contain one cycle for every fixed alpha. That's just basically that you can factor it into these pieces. And the punchline theorem is that every alpha can be factored into disjoint cycles. And this factorization is unique, except in the orders that the cycles appear, because they can commute, right? So you can reorder them.
Disjoint cycles don't move the same elements.
Right. So you can do, I think Fraley has examples in the book of non-disjoint cycles. So there's actually, I believe in Fraley's book, a theorem that says you can always take a permutation and break it up into a whole bunch of 2 cycles. But the 2 cycles won't be, like, they'll have overlap. So some of the elements in one of the cycles will appear in the other cycle. So I'm pretty sure it's Fraley's book that has examples of that. Does that sound familiar?
Mm-hmm.
Okay. It's been a while and I've used a lot of abstract algebra books, so I'm not quite sure if it was Gallian or Fraley, but I think it was Fraley. So you can always break down things into 2 cycles, for example, but they won't be disjoint. But this theorem says that every permutation can be broken up into disjoint cycles, and they all commute. So how do you prove something about permutations? You break it down into prime factorization. Just like you prove things about integers, sometimes you break it down into its prime factorization and then prove it for the primes first, and then you prove it for the product of the primes. That's why this theorem is really important. Some other cool things. The inverse of a cycle is just reverse the order. Cycles are important because they have these properties. So having a disjoint, something broken up into a disjoint cycle, means that now each one of the disjoint cycles have this property. So even though the original permutation might not be a cycle, you can break it down to disjoint cycles and then apply this theorem if you need to. So if you want to do some more, go for it. Prove any one of these. You might. No pressure. So many of you didn't teach today, so I would expect you're not as tired as last week, right? I know you work here, right? You work here on campus, right? So you didn't get a day off. My sister and brother work at Colgate, and they asked me 10 times today, "You have to work today?" "Yes, that's why I'm dropping Anjali off with you." do you have to work today? Like, does everybody have to work today? No, they just brought me into work today. They didn't bring anybody else to work. Huh? No, they're both programmers at Colgate. My brother went here for a very long time.